So welcome to our second video in this series on tropical cyclone intensity change. In this one, as well as our next video coming up after this, we're going to take a look at the effects of vertical wind shear, particularly that associated with flow from the cooler, drier surrounding environment upon tropical cyclone intensity. When we first introduced the necessary conditions for tropical cyclone formation, we discussed how vertical wind shear must be low and the relative humidity within the environment, particularly in the middle to upper troposphere, must be relatively high to permit tropical cyclone intensification and formation to occur. Now we want to talk a little bit about why that is the case. In this video, we're going to focus on the dynamical effects, so primarily that associated with just the vertically sheared flow in the tropics, subtropics, or the mid-latitudes, and not that in conjunction with the environmental thermodynamic conditions. We'll dig into that in our subsequent video. So note that we're going to consider exclusively dry dynamics. We're not going to be worried about complications associated with latent heat release, moisture, things of that nature. So it's going to be a very basic discussion, but keep in mind it's also going to be a very mathematically intensive discussion. There's going to be a lot of concepts that may be somewhat new. So I would encourage you, as we'll do here in our video, to take it kind of slowly and let it sink in a few times as you go through this. So let's take a look at a satellite loop here from Tropical Storm Flossie in the Eastern Pacific, really into the Central Pacific, from the 2017 hurricane season. We have Hawaii here depicted on the west side of the diagram, and we have three different satellite depictions here. Our visible satellite is first, followed by our infrared, and followed now by our water vapor satellite loop. Note that the visible satellite gives us the best indication of where the center of circulation is at low levels. It's on the west to southwest edge of the colder cloud tops that we see within the infrared and the water vapor satellite imagery here. If we look in the mass of cloud that we see here, especially in the infrared image late in the period here, and then into the water vapor image late in the period here, there's some indication of mid-level cyclonic rotation and then on the broader scale outflow or anticyclonic rotation away from the system. And that's associated with the cyclone's intensity being strongest near the surface and then decreasing as you go upward. But note how there is a vertical tilt to this. The low-level center is west and southwest of the mid-level center and the upper-level anticyclonic circulation atop that. So the vertically sheared flow, which you can kind of see through these cloud elements well to the west of the storm here, is out of the west and southwest, leading to convection being favored in what we call the down shear, or down the direction of the vertical wind shear direction, with the low-level feature lagging ahead to the west and to the southwest, up shear, against the direction that the shear is flowing. So we can envision this pretty straightforwardly as thinking about the cyclone as like a cylinder that the wind is kind of toppling over. And we'll build on that concept here in just a moment, but there's some limitations to that contextualization, which we also want to build upon. So let's consider a basic westerly vertically sheared flow, with weak westerly winds at low levels becoming increasingly fast as you go toward the upper troposphere here. If we consider this gray cloud mass to be the core of our tropical cyclone, with strongest rotation given by the thicker red circulating arrows here at the low levels, weakening as you go upward with increasing height, that example of this is sort of like a cylinder, a feature that the wind can tilt over, is what we do initially see. We see that this faster wind takes the top part of the circulation and tilts it down shear or downwind toward the east in this case. So we have the low-level circulation still strongest here further back to the west, and then as you go upward, the center of circulation is found progressively further to the east. And this distance can be on the order of hundreds of kilometers if this is the only thing acting. So if we have a shear magnitude of just 10 meters per second, maybe this wind is 2 meters per second out of the west, and maybe this is 10 meters per second out of the, or 12 meters per second out of the west. So you're looking at something that's roughly 5 miles per hour to 25 miles per hour here. That little of a difference, if there's nothing else acting, spread that out over the course of the day, you're looking at a distance of almost 1,000 kilometers. between the low-level center and the upper-level center, which is really much too large compared to what we typically see, even for shears that are greater than 10 meters per second like we are trying to envision here. So obviously there must be some other processes that are taking place to reduce this tilt. It's still going to be tilted, kind of like what we see here, but this separation distance is not going to necessarily be 1,000 kilometers. It's going to be on the order of 100 or 200 kilometers, as the satellite loop on the previous slide helped to show. So to keep in mind what we're dealing with shear, the shear vector itself is just the upper level wind vector minus the lower level wind vector. So we have this upper level wind vector. If we subtract this lower level one from it, so we take this, place its beginning at the tip here, and that's going to come over to here. And then we draw a new vector from the beginning of the first to the end of the second. That's going to give us our vertical shear vector, which in this case is westerly. The magnitude of that is just the magnitude of that difference here. And that tells you the speed, which in this hypothetical example we've been describing as 10 meters per second. So how can we ultimately reduce that tilt that the vertical wind shear would impart upon the tropical cyclone? There's a number of different ways that we can do so without even invoking thunderstorms specifically. In terms of the vertically sheared flow, tilting the vortex from upright into the horizontal plane leads to specific atmospheric circulations that form. The first class of which is horizontal rotation induced by the tilted vortex. And you probably are asking, what does this even mean? I have a vortex, it's rotating, there's horizontal rotation. I'm tilting that into the vertical. How is there new horizontal rotation associated with that? We'll talk about that in the next slide. There's also vertical motion-induced divergence across the vortex. So if you have flow going across the cyclone and tilting it, it also tends to force ascent, rising motion, downwind or down shear of the storm. And of course, if you have rising air, you have to have something replacing it from below and spreading out from above or up above. And so that leads to patterns of convergence and divergence that go across the cyclone, which, as we'll show, can actually help reduce the tilt induced by the vertical wind shear itself, suggesting that the shear is to some extent self-limiting. We can also consider how thunderstorm heating might lead to the vortex redeveloping. So you have your tilted vortex and convection. Thunderstorms are favored down shear or away from the low-level center. So you get this mid-level center that if that thunderstorm activity is able to spread the heating over a relatively deep vertical column without it getting spread down shear as well, you might actually cause your low-level vortex to jump back underneath the cloud cover and become temporarily realigned in the vertical like so. We're not going to talk about that process here specifically, although the discussion that we have about where vertical motion is favored helps to get at why that might actually come to be the case. There's also a third class of processes dealing with internal vortex dynamics with what are known as vortex-Rossby waves. That's very, very, very deep dynamically. I'm going to refer you all to Reeser et al. 2004 in the Journal of Atmospheric Sciences if you're interested in more detail, but be forewarned, it is some of the most dynamically dense, dynamically deep material that you may come across in the entire atmospheric sciences. So we're not going to deal with that here in the context of this class. So what we are going to focus on, especially in this video, is these atmospheric circulations resulting from the vertically sheared flow. And this idea of vertical motion helps us to be able to understand how the second feature with vortex redevelopment might occur, but we're not really going to touch on that extensively here. So let's talk about this idea of induced horizontal rotation. So we have our westerly vertical wind shear depicted here at left, and it's already tilted the cyclone in the vertical from west to east as you go from low to upper levels. We have our cyclone that is strongest near the surface, and it becomes weaker as you move to the middle and upper troposphere. So the thickness of the red curved arrows that you see here is smaller as you go toward, higher altitudes. So there's a dynamical concept known as action at a distance. This rotation, whether at upper levels or low levels, does not just exist in a vacuum. It's not as if, oh, I'm at 200 millibars, I have cyclonic rotation, but at 180 millibars and 220 millibars, I don't have cyclonic rotation. That's not how the atmosphere works. It's a fluid. It has features that evolve over some distance within the vertical. So when you tilt the cyclone into the vertical, as we're doing so here, or maybe perhaps from your perspective more like this, that cyclonic circulation that's up here at upper levels is not just at that one level. It has that tilt downward toward the surface, but it also has some structure straight up and down within the vertical as well. And this action at a distance idea conceptualizes how that is the case. It's pretty dense dynamically as well. We're not going to get into it much more than we do here. So this rotation is associated with weak induced horizontal circulations in the vertical. So this cyclonic circulation at upper levels is going to have a reflection that extends downward and upward over a particular depth that is governed by how strong the rotation associated with that circulation is, as well as the stability of the atmosphere. If it's relatively stable, it'll be a very short vertical column, as you might see near to the tropopause. But if it's not that stable, it may extend over a greater vertical depth. Likewise, this low-level circulation is also going to be associated with an induced horizontal rotation that extends downward and upward over a depth governed by its intensity, as well as the atmospheric stability conditions. So we'll conceptualize this here at low levels with this yellow rotating feature here with an L depicted here. Note that I've depicted them as weaker, not as thick of arrows as you see down at the surface here, because the magnitude of this circulation weakens as you go away from where that circulation is strongest. So it's a relatively weak compared to the surface circulation, cyclonic circulation at upper levels induced or associated with this stronger cyclonic circulation near to the surface. In turn, this relatively weak cyclonic circulation aloft associated with the tilted vortex is associated with an even weaker cyclonic circulation near to the surface associated with its vertical reflection here. So it too has thinner yellow arrows associated with that cyclonic rotation here. So we have flow. This upper level reflection leads to a southerly flow atop the upper level cyclonic circulation. This induced flow from the circulation here in yellow leads to a flow directed from north to south atop the surface reflection of the circulation. And these two flows can cause the cyclone no longer to be tilted from west to east, but it's going to try to take that upper level circulation up here and shift it to the north. And it's going to try to take this lower level circulation and shift it to the south. So it's going to cause this feature to rotate around. And that's ultimately what that last bullet is describing. But it's tough to kind of take a video camera here and take something and kind of tilt it in all three of our dimensions. So let's take a look at some model output that helps us to visualize this. So we have three different levels that we're looking at here: near the surface, the mid-troposphere, and the upper troposphere near to the tropopause. As we go from left to right on this diagram, note that it's the X direction here. What we're really looking at is increasing time. The system as a whole is moving from west to east, and we have the north-south direction here along the Y-axis. So initially, you have a tropical cyclone at the origin, 0, 0, and all three of these circulations, low level, mid level, upper level, are right on top of each other. The sheared flow has not had the chance to cause these to no longer be in alignment. But as you go forward in time, with the westerly shear flow, you start to tilt it into the west to east direction. But then those induced circulations cause the upper level circulation to be directed from south to north and the low level circulation to be directed from north to south. And that's what we see here with our second time. Our mid-level vortex is roughly still on the y=0 line, but the upper level vortex given by the star is found to the north-northeast, and the lower level vortex is found to the south-southwest, not quite as far away from the star, or from the diamond, sorry, as is the star. So initially it extends these with this low-level vortex to the west, mid-level vortex in the middle, upper-level vortex to the east, and that process with the induced circulations that we looked at on the previous slide causes these to rotate around to the south and to the north at low and upper levels respectively. But then this process continues. If you take this low-level circulation, it again is still going to have a reflection as you go upward, and that's what these yellow arrows are depicting. So this upper-level vortex is now going to feel this east to west flow here. In turn, that upper level vortex is going to have a reflection down to the surface as well. So this surface circulation is going to feel a west to east flow. And that allows us to get from this second time to this third time here, where the upper level vortex has now come around to the west-northwest, and the low level vortex has come around to the east-southeast. And then that continues forward through time. The two are rotating in a counterclockwise fashion around the mid-level vortex. Ultimately, the distance, the separation distance between them that starts out on the order of 200 kilometers, ultimately gets smaller. We can conceptualize this with that third time that we have here. The shear is still from west to east, but now the upper level vortex is to the west and the low level vortex is to the east. So now you have this type of structure, and the shear is going to try to bring it back like this. It actually has created a situation where it's counteracting what it did initially. And so the distance between the star and the cyclone symbol that is relatively large here gets relatively small here. Now, of course, this isn't the only process that's being captured by this sequence of times that we see here, but it helps to show that even when you do get this initially large separation, these effects associated with the induced circulations can lead to a scenario where the tilt changes, not from west to east, but perhaps north to south, and then kind of counteracts what the tilt would initially, or the shear would have initially done. And we call this process precession, as the lower and upper level vortices rotate around the mid-level vortex, leading to a situation where the tilt degree or tilt magnitude is relatively small as we get later on in time here. These separation distances are 50 to 100 kilometers at most as you go forward with that there. So that one is a little bit tough. There's a couple of leaps of faith that we have to make in terms of this idea of circulation not existing in a vacuum and having vertical structure associated with it, and how that can lead to the vortex causing itself to move in different directions than what the large-scale wind would do. This one gets a little bit tougher in this regard as well, in that these circulations can modify the vertical wind shear. So these induced horizontal circulations are not uniform in the vertical, and we talked about that when we first introduced them. So we have our strong actual circulation here at low levels, and we have the weaker induced or associated cyclonic circulation directly above it at upper levels. So there's a reduction in the magnitude of cyclonic rotation as you go upward here. So we can create a vertical wind shear based off of that. This southerly flow becomes smaller as you go up, this northerly flow becomes smaller as you go up. This southerly flow becomes smaller as you go up. And so the shear associated with this is southerly to the west and northerly to the east. And that's ultimately what this diagram is going to show. We have what we know as anomalous anticyclonic shear. You have cyclonic rotation decreasing as you go up. So if you take weak cyclonic minus large cyclonic, you get weak anticyclonic resulting. So at mid-levels, you have anomalous shear from south to north on the west side and north to south on the east side. We can repeat this process for the features at upper levels. So we have our actual circulation here at upper levels, and then we have the weaker induced circulation here at low levels. So if we take upper level minus lower level, we have cyclonic rotation that's increasing with height. So large cyclonic minus weak cyclonic gives us weak cyclonic. And that's ultimately what we depict here, anomalous cyclonic shear. So we have weak flow from north to south, weak shear flow from north to south to the west, south to north to the east. And we had the opposite here on the other side, where we had anomalous anticyclonic shear, which was south to north, further to the west, and north to south here, closer to the vortex. And so this is going to try to take what the shear is, which is initially exclusively west to east associated with the large scale flow, and it creates north-south components of this. We have anomalous northerly shear here in the middle. We have anomalous southerly shear further to the east, and as we showed before, further to the west. And so if you can get the cyclone's tilt to not just be in this west to east direction that we have here, but maybe the features start to rotate around each other, you can modify the shear that the vortex experiences in this way as well. If you have a vortex that's tilted from north to south, that north to south shear that these features are inducing and adding to the west to east shear of the environment now become important, whereas now they probably don't matter all that much at this initial time. So I'd encourage you to kind of sketch this out. Think about this in terms of its next logical step. Take it to the second time or the third time that was showed in the previous set of diagrams. Does this north to south type of shear matter in those cases? And if so, how does it matter? Does it counteract what the tilt would be, or does it add to what the tilt would be? So now we can move on to our last bullet in this dynamical effect, and this is the vertical motion induced divergence. So we start off clean again with our westerly sheared flow that has tilted the vortex in the west to east direction like so. Strongest rotation at low levels, weaker rotation aloft. So if we call this a cyclonic rotation or cyclonic vorticity maximum, this wind, this sheared flow that's out of the west here, is always going to try to increase vorticity or rotation to the east and decrease it back to the west. This is what we call cyclonic and anticyclonic vorticity advection. The wind is going to try to take that vorticity and push it to the east and decrease it back to the west. In general, the magnitude of these advections increases with height. So the wind speed increases, but the rotation strength decreases somewhat. So there's counteracting effects. The magnitude of advection is related to the wind speed advecting the strength of the feature. So we have a faster wind speed, but a weaker feature. The balance between the two favors the stronger wind speed. So you get stronger cyclonic vorticity transport aloft and weaker cyclonic vorticity transport down near to the surface. So this cyclonic rotation transport by the vertically sheared flow here favors cyclonic rotation transport or cyclonic vorticity advection that increases as you go upward. And the opposite is true here on the backside. You have greater cyclonic vorticity transport away at upper levels than you do at low levels. So you have negative cyclonic vorticity advection or anticyclonic vorticity advection that increases as you go upward here to the west. From a mid-latitude perspective, cyclonic vorticity advection that increases upward is associated with forcing for ascent through that column. Anticyclonic vorticity advection that increases upward is associated with forcing for descent as you go back onto the west side of the storm. Those of you who are juniors will be introduced to these concepts next year, whereas these for seniors and grad students are probably secondhand at this point. But of course, if we have rising motion here and sinking motion here, we need air to flow away from where the air is sinking at low levels and into where the air is rising at low levels. And the opposite is true here at upper levels. We need air to flow away from where there is ascent at upper levels, and we need air to flow toward where there is descent at upper levels. And so we can add in those lines here in blue to show that flow must diverge out of the region of descent at low levels and converge into the region of ascent at low levels, and it diverges from the region of ascent and converges into the region of descent at upper levels here. So we get divergence-induced flow across the vortex. It's trying to take this upper level vortex and shift it back to the west. And it's trying to take the lower level vortex and shift it off to the east. This counteracts what the vertical wind shear is trying to do. So it's trying to take something that's tilted and bring it back closer to the vertical, just as we saw with some of the other schematics, although this one is perhaps a little bit more straightforward to conceptualize once we know that we would expect there to be rising motion to the east in this case and sinking motion to the west in this case. So we can take a look at model output to try to confirm this for ourselves again. These lines that you see here in the solid contours are associated with a measure of the vortex intensity. So it's strongest near to the origin, 0, 0 on the diagram, and it becomes weaker as you move further away from the center, as we would expect. The wind vectors that you see here that are predominantly directed away from this point here at about 100 kilometers to the east and toward this point here that's about 100 kilometers to the west is looking at the upper level wind, and in particular the divergent component of the wind. So that's exclusively associated with divergence or convergence. And so we see rising motion here to the east with the westerly shear leads to air diverging away at upper levels, and the descent that is back to the west leads to air converging in at upper levels. So at upper levels, you get this flow from east to west across that vortex. That's going to again try to tilt it back into the vertical, as we have seen on the previous slide. Of course, that's not all that the vertical motion does. It helps to induce thunderstorm activity, yes. It helps to induce patterns of divergence, yes, both of which can help reduce the tilt of the vortex. But also the vertical motion can help induce potential temperature anomalies as well. And the interplay between the vertical motion and potential temperature anomalies has important implications for the structure of the vortex and continued persistence of the down shear favored vertical motion, down shear favored ascent in particular. So as we discussed on the previous slide, this westerly shear here initially results in ascent to down shear, or to the east in this case, and descent up shear, or to the west in this case. Of course, in the absence of diabatic heating, air will typically conserve potential temperature as it moves. So neglecting latent heating, neglecting radiation, neglecting surface heat exchange, things of that nature. So adiabatic flows, just like on a SKU-T, we go up the dry adiabat or down the dry adiabat. So when you do so, potential temperature does not change because the potential temperature is defined by that dry adiabat. So in the absence of those diabatic heating processes, air will conserve potential temperature as it moves. So let's throw on a few isentropes here. Theta 1 has a value maybe 290, 300, 310, 320 Kelvin here. These are depicted such that potential temperature increases as you go upward, the common situation within the atmosphere. So if you have ascending motion here to the east, air that starts out at theta 1 is going to try to maintain theta 1 in the absence of diabatic heating as it goes upward. So it's going to try to tilt these lines upward on the right side. Likewise, here on the left side, back to the west, air that starts out aloft here with the potential temperature near theta 4 is going to try to keep that as it comes downward. So it's going to try to tilt these lines downward to conserve that potential temperature. And so we end up with this type of structure depicted by the dotted lines here. The isentrope slope from bottom left to upper right as you go from west to east across the cyclone, exclusively due to these vertical motion anomalies that we have depicted here. So at any given height, for instance, this height here of our third wind vector on our diagram, the potential temperature value to the east, here between theta 3 and theta 2, is less than that to the west, here roughly being theta 3. So it's relatively warm to the west and relatively cold from a potential temperature standpoint to the east at any given altitude, height or pressure based across the tropical cyclone. So we get this low potential temperature anomaly, relatively cold here to the east with our ascent, and high or warm potential temperature anomaly co-located with our region of descent to the west. So we can look at this in the horizontal plane now. We have north-south on our y-axis, east-west on our x-axis, and we have our cyclone given by the universal hurricane symbol with cyclonic rotation associated with it. And we're considering westerly shear, so we have forcing for descent to the west and forcing for ascent to the east, which creates those cool and warm potential temperature anomalies. So on any given horizontal surface, it has a relatively low potential temperature to the east, relatively high to the west, and so that's how we can get these four isentropes that we have depicted here. Smaller to the east, higher to the west. So again, absent diabatic heating, air is going to conserve potential temperature as it moves. So here to the east, starting straight to the east, it's relatively cool and it's going to try to keep this value that is less than theta 1 as it starts to move toward the west around the north side of the cyclone. Conversely, to the west, an air parcel that has a potential temperature that's greater than theta 4 is going to try to keep that value as it moves to the east on the south side of the cyclone. Because potential temperature increases as we go upward, as we depicted on the previous diagram, if we did a vertical cross-section through this, theta 1 would be found below theta 4 as you get over to the west. And likewise, theta 4 would be found above theta 1 as you come back to the east. So to keep something that has a value of theta 1 or lower, you're going to have to descend below theta 2, below theta 3, below theta 4 as you go from east to west. Likewise, to keep a value that's at or above theta 4, you're going to have to ascend above theta 3, 2, and 1 as you go to the east on the south side of the cyclone. So this flow creates anomalies of vertical motion in and of itself that are out of phase with what we initially saw. We had forcing for ascent to the east, now we get forcing for ascent to the south. Here we had forcing for descent to the west, now we have it to the north, associated with the potential temperature anomalies that the initial vertical motion anomalies created. So we have this change. They start off, vertical motion and potential temperature lead to identical temperature anomalies or co-located temperature anomalies, but then once you have those temperature anomalies, suddenly they become out of phase because of this idea of potential temperature being conserved as air parcels move around the cyclone. So we can see this in the context of model output once again, 24 and 48 hours after vertical shear has started to affect a storm. We have our different symbols here. We're looking at vertical motion on the left set of diagrams and potential temperature anomalies on the right set of diagrams here. Our tropical cyclone is tilted in the east-west direction here at 48 hours, or 24 hours, sorry, and west or south-southwest to north-northeast at 48 hours. But note how we have a ascending anomaly to the south and descending anomaly to the north, where we initially had ascending anomaly to the east and descending anomaly to the west. They have rotated clockwise by 90 degrees relative to what we initially expected. And between them, we have our warm and our cold anomalies. So as air goes down, so we can think about air rotating cyclonically from east to west around the north side of the cyclone. As it's forced to go downward, it has to become warm. As it's forced to go upward, it has to become cold relative to its surroundings. So we get a warm anomaly between the down and up, and we get a cold anomaly between the up and down. 90 degrees out of phase once again. These features then rotate around each other. I apologize for this text box getting a little bit cut off here, but over time the cyclonic flow not only does it go through these anomalies, but it also rotates the anomalies. So our down anomaly goes from north to west Our up anomaly goes from south to east, and the warm and cold anomalies here, cold anomaly rotates 90 degrees to the north, warm anomaly rotates 90 degrees to the south. They maintain their relative orientation versus each other once they have formed, but they rotate around each other in this cyclonic fashion, at least in the context of this dry dynamical perspective. Typically, however, the ascending anomaly is favored down shear, so in this case to the east, and slightly to the left, so sort of toward the northeast of a westerly vertical wind shear vector. And this is where convection and ascent are typically favored. The reasons why that ends up becoming locked in place are a little bit beyond the scope of what we wish to talk about here. Part of it's because of the inclusion of moist processes. Part of it's because we do have that constant vertical wind shear forcing. It's not as if it happens initially and then the vortex evolves on its own after that point in time. But still, in the absence of all of that, we can see how these features would rotate around each other and lead to ascent being favored in different locations over the course of time. So wrapping everything up, we've covered a lot of ground here. We've talked about a lot of different concepts here. At the most basic level, the vertical wind shear tilts that upright vortex down shear from west to east, as we depicted for westerly vertical wind shear. But there's a myriad of factors associated with induced or associated horizontal and vertical motions that can reduce this tilt. It could even increase the tilt in some particular configurations, but in general, it helps to reduce the tilt in one of several ways, whether that be through vortex rotation, the induced horizontal circulations that shift things around so that the shear counteracts what it initially did, a modification to the shear itself associated with the change in intensity of these features with height, as well as vertical motion-induced divergence that can take a vortex and try to tilt it back against the vertical shear that it was otherwise experiencing. These induced vertical motions that are tied to those divergence anomalies also create potential temperature anomalies that, as we showed, can feed back upon the induced vertical motion field. So you get vertical motion and potential temperature anomalies that are in lock phase with each other initially, but once you get those potential temperature anomalies, you shift the vertical motion anomalies 90 degrees away from them, and that structure is maintained as you go forward through time, assuming that nothing else changes. And this can modify where thunderstorm activity preferentially occurs, presuming that those features continually rotate around the vortex, which they ultimately don't, at least not entirely speaking. So in our next video, we'll discuss vertical shear in a little bit more detail, but we'll focus on the thermodynamic impacts. Vertical shear helps to bring environmental air into the tropical cyclone environment, and that has very strong influences on the intensity of a tropical cyclone. So until then, thanks for tuning in.